Okay, before we start today, we are not going to start with any icebreaker. We will jump into a revision of linear regression. What is linear regression? And we will look into something called gradient descent. And with that, we will move into the regularization techniques. Right? We will look into something called the ridge and the lasso regression. Uh, if time permits, we will look into elastic net as well, which is another regularization technique. But we will mainly focus on these two today. And tomorrow we will be doing a end-to-end regression project. How to perform analysis on top of our data, the EDA, with the data cleaning, and then we will look into um, training and testing. We will look into something called cross validation followed by prediction, right? So this will complete the entire life cycle of a regression problem. We will also try to wrap this up and start with our next um, algorithm, which is logistic regression. There we will talk about something called the confusion matrix. We will talk about the basics of logistic regression and so on. So today I might have to leave a little early, as today is my wife's birthday, so we have to plan something out. And yeah, let's start. So if we remember what is linear, before we start, if you have any question, do let me know. Okay, rather we can start, and if you have any question, do let me know in the chat. Okay. So if we typically draw a set of numbers on a piece of paper or a graph, and we randomly select some points x and y, it will look something like this, right? And now if you wish to draw a line, we can draw a line which will basically pass through these lines, and as we have discussed, we will try to minimize the number of the errors, right? And someone can draw a line like this, or you can draw a line like this, right? Or you can take just the mean of all these numbers and can draw a line which is exactly parallel to the x-axis, which is the mean line. So for example, the mean is 3.5 of all these data points. So we have a mean line, which is this, right? Now, when I said, these are the types of lines, so I might draw a line like this. Another person can draw a line like this, or Bhargav can draw a line like the third one. And the worst line which someone can draw is the mean line, but that's okay, right? Now we can measure how well this line fits the data by seeing how close it is to the data points, right? So now we all have understood in the last class that if this is our predicted line, we can basically find the difference between the absolute actual value and the predicted value. Now if you have x1 and y1, what you basically find the distance between the point and the line, right? This is your predicted, so this part is your predicted one, and this is your actual one, right? Likewise, you find the distance between the second point and the line, right? And so far, if you just take two of these points into consideration, you have basically taken the difference of the first one, right? This b minus y1 and b minus y2, and you basically sum them up if you want to calculate the total distance, right? And this is the sum of the two distance. So this two b minus y1 plus b minus y2 is the sum of the two distance. Now with that, you move on to the third one where you have b minus y3, and you add the third distance to the total sum, and so on. So you'll keep on adding, right, one by one. Now if you can carefully see that these 3 points, right, lies at the lies below the particular predicted line, right? And this particular line, which is the first after the 3, is actually above this line, right? So obviously, if the distance is going to be negative here, or you take a positive here, this is going to be negative and vice versa. Now, if you have the fifth line, which is too far away from this line, it is a even worse situation, right? Because it is too far from the predicted. And when back in the day, we statisticians started working with this type of analysis, they used to take the absolute value. You can see the absolute values. They started using taking the absolute value, and it becomes a little tricky because you are not able to find out which type of which points are far away from the predicted line. And to make sure that then they give penalty to the points which are too far away from the predicted line, they end up squaring the terms, right? They started squaring the terms instead of taking the absolute value, right? And it also ensures that the ultimate value which we are getting is positive, and we are also penalizing the points which are far away from the predicted line. Now, if you have all these points and if you take the difference from the line, so the line is B, okay, the line is B. And if you just take the difference between B minus Y1 and B minus Y2 up until B minus Y9 and take a square, that is actually something we call the squared error, okay? Not the mean squared error now, but the squared error, okay? This is a measure of how well this line fits the data, right? So this is the worst line which you can draw is by just creating a mean of all the data points. You took the mean of all these data points and it came somewhere around 3.5. So you have drawn a line at 3.5 and have taken the distance from 3.5, right? And suppose it came out to be say 24.62. And this is the measure of how well the line fits the data. Now this is called the sum of squared of residuals. We all understand now this is the residual or the error. So we can either call it the sum of square of error or sum of square of the residual, because the residuals are the difference between the real data and the line, right? The predicted minus the observed values, right? And we are summing the square of these values. Now let's see how good the fit is if we rotate the line a little bit. So now instead of a line which is mean, you have created a line which has been tilted a little bit or rotated a little bit. Now you calculate the sum of squared residuals again with the same method which we did, and it came out to be 18.72, right? It came out to be 18.72. In the last scenario, we had the sum which is 24.62, right? And in the last class we discussed, as the error decreases or it is as close as to 0, the better the model will be, right? So now we have, once we rotate this line, we have the sum of squared residues as 18.72, and this is better than the line before we have seen, right? And as we rotate it more, we can see the sum of the squared residuals is getting decreased. So now it is 14.05 instead of 18 point something, right? And what if we rotate the line a whole lot? Okay, so we keep on rotating the lines as as number of squared of residuals decreases, right? And we keep on rotating the lines, and once we rotate this line to further level, what we get is the square residuals now has eventually increased again, right? So the squared residuals is 31.71, so which is obviously greater than 14.05. So with the number of the diagrams which I have shown you, the best is probably this one, right? The sum of squared of residuals 14.05, right? Now, if we just look into a generic line, right? A generic line equation is y equals to ax plus b, or you can say y equals to mx plus b. Someone can say theta 1 x plus theta 2. All it's same, right? Y is your uh, b is your intercept, x is your slope, and y is the value which you want to find out, or we rather call it the dependent variable, right? We want to find the optimal value of a and b so that we minimize the sum of squared residuals. So that is the entire background behind this, that we want to find out a particular value of A and a particular value of B where the sum of squared residuals is the lowest or the minimum, right? Now, if you carefully look into the sum of squared residual, we had something called B minus Y1 square. And with that, the equation of the line is y equals to mx plus c or ax1 plus b. So we have just replaced this value with the equation. Okay, nothing else. So this is the value of the line at x1. So if this is your x1 point, so the equation is going to be y1 is equals to ax1 plus b. Just give me a second. Okay, so this is ax1 plus b, and then x2 is going to be, if this is the x2 point, we are having y2 is equals to ax2 plus b, and so on, right? Now y1 is the observed value here and at x1. Okay, so y1 is the observed value. I'm not sure why my pen tab is not working. Okay, no problem. So since we want the line that will give the smallest sum of squares, this method for finding the best values of A and B is called the least square, right? This method is called the least square. So if someone asks you what is the equation of a least square, you can say that the difference between the predicted value and the observed value, the sum of the squares of the predicted value and the observed value. Okay, that is the least squares. Obviously, we can now understand why it is called a least square, because we want the minimum value of the difference between the squares of the predicted and the observed value. Okay, now we all have got this number, which is 31.71. We have 14.05. We have 18.72, right? And if we plot these numbers over a graph, you can see as we rotated the line, the 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 sum of squares basically reduced, right? It came to somewhere around 14 point something, and after that it again increased, right? So as the slope, so this is the slope, so sum of squared of residuals, I'm plotting this sum of squared of residual with the slope. So as the slope increases, see this, if the slope increases, what happens is your sum of squared residuals will decrease and will again increase. So from this graph, you can understand that this is the point where my sum of squared is the least, and it is for a particular slope. It is for a particular slope. So this point is actually the point where you can say it has the optimal value, right? So how to find the optimal rotation for the line, you have to basically plot the numbers on a graph, and from that graph you will find the optimal value. Obviously, you now understand it as you increase the slope, the slope might decrease and then it will increase, and it will follow the same pattern for any scenario. Okay, now if we take the derivative of this function, that derivative tells us the slope of the function at every point, right? If you take the derivative of function, it will basically give you the slope. What is the slope? Slope is how steep the curve is. Okay, how steep the curve is. I'll show this in the next slide, that as and when you take the derivative, you will understand the steepness of the particular line. Okay, and as it says that this is the optimal point where you have the least squares. You have the least squares. Okay, and again, if you increase the slope, the line will again get steeper, right? So what we are doing, we are basically finding the optimal value of the slope and the intercept, nothing else. We are trying to find the optimal value of the slope and the intercept. Now, if we want to, showcase this over a 3D graph instead of a 2D graph like this, what we have is we have a curve like this, right? As and when your slope increases, so here your slope is increasing, you will get an optimal point where you will have uh, the minimum sum of squared of residuals. And with that, you can see if this is the curve. I've drawn this on a hyperplane. In this hyperplane, you have a curve. You have a point where the the sum of squared is the minimum. Imagine this as um, a U-shaped, you know, um, U-shaped utensil or something like that. Okay, if you drop a ball, it will probably roll down and will go up, and it will again roll up and down and up and down until it reaches a equilibrium at a point, and that point is your global minima. Okay, that point is your global minima, or the point at which the sum of squared is the least, and that line is going to be the best fit line of your model. Okay, that line is going to be the best fit line of your model. You can see here that the steepness of the particular line is optimal. Okay, and now this cannot be solved using a pen and paper. We have to basically use either a statistical tool or a programming tool in order to find out the global minima, and we can easily do this with Python. Now we want to minimize the square of the distance between the observed and the predicted value. Now we do this by taking the derivative and finding where it is equals to 0. Wherever the derivative is equals to 0, we can say that um, we have reached the global minima. Okay, and this is the point, or this is the point where we'll take which will give us the optimal value of A and B, or rather the intercept and the slope. Right, so this is going to be the line where you have the best uh, optimal value of A and B. Is, for example, if you say that this is the line, the equation of the line is y equals to 0.77x plus 0.6x, so it means that at the global minima your you know um, slope is 0.77 and your intercept is 0.66. Okay, before we move on to the regularization part, any question, do let me know. If you don't have any question, can you move on to the next part?
Yes.
Okay, can you explain again on global minima? Sure. Just give me a second. All right. Okay, let's understand this in a slide. Okay. Now, as I said that, if you have an X and Y, so if you have X and Y, right, you can draw a best fit line as you want. So if, for example, if I have this many points, I can have a line like this, you can have a line like this. Someone else can create a line like this, or a fourth line can be this. Now, how to understand which one is the best fit line? Best fit. Which one is the best fit line? Now, to understand this, we have to find out the optimal value. So if you have y equals to mx plus c, so m is your slope and c is your intercept, right? Now, what you want to do is, you have to basically find out the optimal value of slope and intercept, right? Now, if you take the first line, say for example, this is your first line. With this line, you basically find out the difference between the predicted. So this line is your predicted line, right? And these points are your observed point, right? So you basically find the distance between the line and this point, right? And you get a value. Say for example, after creating, and the square distance. So if the square distance is say, 1 second. If say for example, this is your x1, y1, right? And if this is your predicted value p, in p1, say p2, you have p3 and so on. So basically you will find the difference between p1 and x1, right? And then square it plus p2 minus x2, and you square it, right? And you got a value, say 13. And with the line second line, you got a value. So with line first line, you got 13 as the least squares, or sum of squares, okay? And with line L2, you got 15. With you got 10. With L3, you got say 12, and with L4, you got 70. Now, if you want to plot these points, okay, over a graph, what you can do is you can create a graph where you have slope at one side, right? And you basically take the differentiation. Sorry, you have the sum of squared value, and you have the slope, or rather the derivative of the slope, and you plot this point. So for example, if you have 13, you plot it on 13. If you have say 10, you plot 10. Again, you have 12, and then 17, right? So this is your point: 13, 10, 12, and 17. Now, if I draw a curve like this, you can see you get a U-shaped curve, right? And this is called your gradient descent. Okay, this is called your gradient descent curve. Now, this is the point where the value of this curve is the minimum, right? And this is called your global minima. Why it is called global minima? Because the slope is 0. The dy by dx value is 0. We will not go into the mathematical calculation of it, but just to give you the intuition behind it, you have to understand this is the point where you have the best optimal sum of squared, and this optimal square will basically give you the optimal value of slope and the optimal value of your intercept. Okay, any question? Okay, so we'll move on to, so as you understood that since you got the optimal value of your slope and your intercept, you can just put the optimal value 0.77x and 0.66. Okay, we can calculate this using a statistical tool or a programming tool, and we will probably do this with our exercises. Next, we will move on to regularization. Now, first we will look into something called a ridge regression, regularization. Okay, Now, to understand what is the difference between, why we need a regularization technique. Now, first understand one thing, that in the first graph, we can see that we have something called a underfit scenario. Why we call it an underfit scenario? Because it is not fitting the entire line, in a correct way. Because there are some points, which are too far, right? Some are, too close, and this is more or less a underfit scenario. Okay. Next is where we have overfit, where it is trying to, fit each and every line. It is trying to fit each and every line. Okay. But if we want, some a balanced fit, okay, if this is underfit and this is overfit, there has to be something in the middle, right? There has to be something in the middle. So we'll try to balance this, underfit and overfit scenario. With a balanced fit, you can say that the line will, eventually pass through the mid of all of these points without, either going, touching each and every points, or ignoring some of the points. Okay, so this is your balanced fit. If I want to showcase this with an equation, you have y equals to mx plus c, where, age uh, is the variable, or this is the independent variable, and this is your dependent variable. This is your intercept, and this is your slope, right? If I create a very complex, solution, or very complex equation, it will have, this is called a first degree equation. You'll have, polynomial equations where, you'll have second degree and higher order degrees. So that is not, something which will look through a linear regression lens. Okay, in linear regression, we only will look into scenarios where we have first degree equation, which is y equals to mx plus c. Okay, now if we want to, make this simpler, I have to basically get rid of, the higher dimensions, right? If I get rid of higher dimensions, uh, dimension 4 and dimension 3, what I got is a balanced fit. Okay, let's look into this in details. Okay, so if I remove theta 3 and theta 4, and make it, close to 0, what will happen is I will get a graph which is, a balanced one, neither underfit nor overfit. Okay, now we will look into a simple example that shows the main ideas behind a ridge regression. We'll go into the details about how ridge regression works. We'll show how, ridge regression works in a variety of situations. And lastly, we will we'll talk about how ridge regression can solve the unsolvable problems. Okay. Now we have collected, weight and size measurement of a bunch of mice. If we are in a lab, and we have a bunch of mice, we can, identify uh, the weight of the mice based on the size. Okay, or rather we can identify size based on the weight. Okay, and these are some of the points which we have got. Now if we look into the data, we can use, linear regression, or also we can now say it is a least square method to model the relationship between the weight and the size. We can basically model the relationship between the weight and the size using linear regression, also known as least square method. Okay. Now, what we will try to find out through linear regression is we want to minimize the sum of squared residuals. We want to minimize the squared residuals as much as possible. Okay, and we will identify whether the line which I have created just now is the best line, or, any other line will be the best line. Now, if we, solve this using if we take all the points into consideration, we will find a, line which is 0.9 plus 0.75 into weight as the best line or the equation of this particular line. Okay. Now, when we have a lot of measurement, we can be fairly confident that least square line accurately reflects the relationship between size and weight. But what if you don't have much data? Okay. If we introduce more data into the line, into the graph or into the data set, eventually your training will fail in the testing, right? So what if you have very less amount of data in the training data set, right? Say we start with only two measurements. Okay, out of all these points, we start with only two measurements. Okay, and we have to find the line. Okay, obviously you can say that, you know, if we draw a line which fits or goes through all of the data points, which is the two data points here, this is the best line, and obviously this is going to be the best line. Yes, this is from a StatQuest. So StatQuest is one of the best YouTube channels to, you know, go through the concepts of regression and classification, and we will try to, you know, learn as much as possible through the contents which are already available. And I have also learned from StatQuest a lot, and it is very easy to explain, right? Okay, I will share the link at the end of the, you know, class, where you can understand better about, you know, linear regression or all the other techniques which are required. But StatQuest will basically focus from a statistical point of view. You have to still go through, you know, Python based example, which StatQuest doesn't, you know, covers. Okay, so we find a new line with least square. Now, since the new line overlaps the two data points, the minimum square residual is 0. Obviously, if we want to find out, you know, the sum of square, if this is x1, y1, and this is x2, y2, right? And this is your predicted point p1 and p2. Obviously, you can understand now that x1 is equals to p1 and p2 is equals to x2, right? So there is no difference. So that's why when we take the sum of squares, x1 minus p1 square plus x2 minus p2 square, we get 0, right? Because both of them are same. So the value is 0. So you can say that this is the best line. And if we draw this, we end up with a formula of 0.4 plus 0.3 into weight. Okay. Now, if we try to plot this, or if the green ones are our testing data, what we are seeing that, you know, whenever we introduce the testing data set, the line is very, you know, underfit or overfit for this scenario. Okay, because it is working very well with the training data set, but ideally not working well with the testing data set. And with this data point, we can understand that there should be a line which is like this line p2, which should have, you know, ideally been the best line. So we have the red dots as the, you know, training data and the green dots as our testing data. Now the sum of the squared residuals for just the two red points and the training data set is small, and this in this case it is 0. Now if you try to find out, you know, the distance between these points from the predicted line, okay, this is large, right? These points, the difference between these points are large, right? And if we have large errors, obviously we will not be able to predict the test data accurately. Okay, it means that the new line has a high variance. Obviously it has a high variance because it is too far away. It varies too much, right? From this line, if we say this is the mean line, it varies too much from the mean line or the best line, right? So it has a high variance. This line has a high variance. Now in machine learning, we call this as overfit. We have all known that we all know that whenever we have you know we have points, and if it passes through all of these points, we call it as a overfit scenario. Here in the testing data set, you can see or a training data set, you can see it passes through all the points, right? So this is the overfit line. This is the overfit line. Okay, we will go back to the training data, and since we have a high variance, um, it is a overfit scenario, and we will try to bring in some bias in the data. We will try to bring in some bias in the data, and which is the main idea behind a ridge regression. So it will make your line uh, less steeper. It will make your line less steeper, right? So earlier your line was this green line, and now you want to create a line which is a blue line, which will introduce some bias in the data. Bias in the data, right? You introduced some bias, right? And this will eventually lower your variance. As we all know that this data set was having a high variance, right? So if you tilt this line a bit, right? If you tilt this line a bit, now your variance is getting reduced, right? Your variance is getting reduced. So if you introduce a little bias in the data, right? If you introduce a little bias in the data, you are getting a lower variance in the testing data set as well.
One question here.
Right.
Yeah. So here that whenever we are measuring the error,
Mm-hmm.
it is absolute value or it is squared value. So we don't know if the the point was up or down from the line that we drew, right?
Mm-hmm.
So when you say that we are tilting the line or we are
Mm-hmm.
rotating, how
Mm-hmm.
do we know how does algorithm know in which direction to tilt?
No, it will basically tilt your point, tilt your data. So it works like this. So you, for each degree rotation, so your current line is this, right? Now it will tilt like this, and this, and this, and this, and it will tilt till you get a 360-degree view. Okay. And out of these point, it will try to find out the best line. Out of this line, it will try to find out the best line. Now, with the best line, as I said earlier, you basically find out the least square value, then plot it on gradient descent, and from that gradient descent, you get the derivative of that particular slope, and wherever it gets a global minima, right? And it takes that line as the best line.
This what you said, rotating 360 sounds more like brute force rather than.
Yes, it does, but ultimately the entire logic behind um, regularization is to introduce a little bias so that your variance get lowered in the testing data set. Okay, and for that you have different techniques, right, which basically works in the background. And when you say brute force, I will come that to explain it in a from a practical point of view. But for now we have to understand that as steeper the line is, that there is more chance of introducing you know high variance in the testing data set. Okay, so we want, with ridge regression, we want to make this line less tilt.
Yeah, I'm not asking only regarding ridge regression.
Okay.
This line that we have, the fitting line, we have in linear regression as well, right?
Right.
Yeah. So in that also, I think we discussed that we are taking mean square error.
Right.
So that is also not any does not indicate any plus or minus. How, I mean, is error more or less? So in that also, I'm basically, I'm not understanding how we are taking the decision that we should increase the value in input, the slope, or decrease.
Right. So when I will introduce the, linear ridge regression equation, so we'll have a lambda value which will basically govern, and that lambda value which will eventually in advanced classes you will understand this is the learning rate, and basis that you will be able to find out which is the optimal value.
Okay.
Okay. Let me just go through the ridge regression, and if you have then a question, do let me know. Or else we might, confuse other folks. Okay. Now, this is the bias we introduced in the data set, and with that bias, what happened is our initial line got tilted a little. Okay, we tilted this line. What it will do is it will lower the variance in our testing data set. Now, if you look into this data, what happens is the distance between the predicted value and the observed value is less, right? Obviously, the distance is less, so that's why the least square values here, the least square value will be less. Now, in the training data set, you will see that this is not actually fitting both these points which are present here, this point and this point. So it is slightly worse fit, but it will provide you a better prediction in the long term. Now let's look into the ridge regression equation. Now we all know that the equation of a line is basically y equals to mx plus c, right? So m is your slope and y is your intercept is your c. Now it minimizes the sum of the squared residuals. Okay, that's fine. Now, one second, I have to plug in my charger. Okay, so we introduced with the sum of squared values, we introduced something called the lambda and the slope square. Okay, lambda and the slope square. If you take slope as m, so we introduced lambda into m square. So with y mx plus c, right? M is your slope. So we introduce something called lambda into m square. Okay. Now this part of the equation adds a penalty to the traditional least square method. So this is the point where you are adding a penalty. Okay, if this graph is or the line is steeper, you add some penalty to the point. And lambda is determined the how severe the penalty is going to be. Okay. Now to get a better idea, we will look into some of the numbers. We'll look into some of the numbers to understand this better. Now the equation of the line, the original line was 0.4 plus 1.3 into weight, right? This was the equation of the line, right? And since this is the least square fit, there is no difference between the predicted value and the observed value, right? So that's why the ultimate least square value is 0, and the slope value is 1.3. So ultimately we will add 1.3 square as the value, and we'll take lambda is equals to 1 for now. Okay, and all together we have something called something with 1.69 as the penalty value. So what happened is you have y equals to mx plus c as the equation. Now I said, with ridge regression, you will basically have the sum of squared value, okay, plus the lambda into your slope square. Now sum of squared value here is going to be 0 because this is exactly on point, right? There is no difference between the actual point and the predicted point, observed point and the predicted point. So this is going to be 0. And then we have taken lambda value as 1, and the slope for the particular line was 1.3. So 1.3 whole square. So it comes 1.69. Now with the introduction of this number, right, the slope or the equation of the line changes. The equation of the line changes to 0.9 plus 0.8 into weight. And you can see that, the line has become a little less steeper. And this is what the ridge regression does. Now with this line, if we take this line into consideration, we have for this line P2, the difference between this point and this point, if we take it is 0.3, right? And the distance between this point and this point, if we take 0.1, lambda if we take 1, and the slope is here 0.8. And if we do the math, right, we get a value of 0.74. Okay, which is obviously less than the previous one, less than the 1.69 value, right? Now you can see that the value has bettered. Thus, if we want to minimize the sum of squared residuals plus the ridge regression penalty, we would lose the ridge regression line over the least square lines. We would choose the ridge regression line over the least square lines. As I said, the value has bettered eventually by tilting the line a bit, making it less steeper. We will take this line as the better line, right? So what happened is with the introduction of a small amount of bias in the data, right? We created a penalty, and it has basically worked well with the large amount of variance in the data. So if we don't have any small amount of bias, it will probably not penalize the 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 data points. Now when we added a ridge regression, as I said, it introduces a small bias, and due to that due to the penalty, it has less variance. Okay, so we will look into how ridge regression penalty affects the particular line or the data. If we want to keep things simple, we imagine that this is a best line for us, and as and when you can see that the difference in the weight here, the difference and weight here. So if I talk in mathematical terms, this is tan 45, right? Or okay, don't want to go to the mathematical. So if this is the best line, if we have with 1 unit change in the weight, the size also increases by 1 unit. It is exactly similar, right? And as we make the steep, uh, as we have a steeper line, what happens is that with what 1 unit change in weight, you have a huge difference, right? you have a huge change in the size. See, with this much change, you have a huge change in the size, which is obviously not good, right? So as and when you make the line less steeper, okay, if you make the line less steeper, the changes are also less. Okay, the changes are also less. Now this is what has happened with the ridge regression. With ridge regularization or ridge regression, you basically make this line less steeper, and with less steepness in the data, with each change in weight or each unit change in weight, now the change in size has also become optimal, okay, or has become less. So the ridge regression penalty resulted in a line that has smaller slope. And this is what a ideal scenario would be, that with each uh, unit change in weight, the size will also be changing, but with much very less variation. So this eventually means that ridge regression lines are less sensitive to weight than a least square line. Okay, so we have made the the data set less sensitive to any sort of bias or um, bias which is introduced, which will eventually lead to less variance in the data. Now lambda can be from any value from 0 to a positive infinity, right? And the sum of the squared residual is and the equation of a regression line is sum of the squared residual plus lambda into slope square. Now if the lambda value is 0, obviously there is no difference between a least square line and a ridge regression line, right? So that means that the ridge regression line will only minimize the sum of the squared residuals. Yes, how to decide the lambda value? So lambda value is something which is iterative, right? You have to, have a value which starts from 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 anything more than 0, and it will increase with each iteration. So if we create a for loop, for example, which each iteration it should change by 0.001 or 0.01, and eventually we'll try to find out the best number out of that data. We'll do this in Python, so don't worry about it. Okay, so when we show you the practical example, we will be able to find out which is the best lambda value. So we'll try to increment the values as and when required, because we will not be able to change the intercept value or the slope value. It will be, the equation is created in such a way that it finds the um, optimal value of lambda of the intercept and the slope by tuning in the lambda values, right? So we have the sum of squared residuals plus 0 because we took lambda is equals to 0, right? And when we took lambda equals to 0, you can see the least square line and the ridge regression line both are same. Both are same. Okay, so there is no difference between a ridge regression and a least square line when the lambda value is 0. Okay, you might be asked this type of question in interview. Now moving on to the next one, we set the lambda value as 1. Okay, and when you set the lambda value, so this is a very hypothetical scenario. Okay, don't come to a conclusion that if we have lambda equals to 1, we will have a line something like this. No. So this is just a practical hypothetical scenario where if you set lambda value equals to 1, obviously it is going to be better than the least square value. okay, or worse than the least square value, or whatever it is, but it will not be same as the least square value or the least square line. Okay. Now, if you change this lambda to 2, it will again be a little less steeper, right? You can see the difference. It is getting less steeper, and which set it to 3, it becomes more or less steeper, right? And when we create a value which is, lambda equals to say 100,000, in that case, what happens is it will ideally be mean. It will be either be the mean of all these points. Okay. And as and when you increase the value, it will rotate 360, and which was mentioned earlier as brute force. But we will not go into brute force for now, but we'll move to the simpler explanation. So you understand now that, with lambda equals to 0, you will have a line which is aligned to least square value. With 1, it will become less steeper, and so on, right? And so how will you decide what value to give lambda, right? So a question which was asked earlier. So our patience has played well. We will now see how we can decide the optimal value of lambda. Now we will try to, fit in a bunch of values for lambda. As I said, we will iterate through, loops and lists to increase the value of lambda to find out the optimal value. And we will use something called the cross validation technique, which we'll learn in the next class, cross validation technique. And we will use, here it is mentioned tenfold, but we'll use more than that also, in order to determine which one results in the lowest variance. So our main task is to make sure that in the training testing data set, there is the least variance in the data, right? There is the least variance in the data. So you have to use something called a cross validation technique. And this will be asked in the interview, right? If you say, I know, linear regression, they'll probably start with asking you questions about um, least squares, okay, cross validation. Um, um, they will ask you question about ridge regression, lasso regression, and so on. Okay. So yeah, so we will determine which one is the lowest variance. Now we'll move on to something called a lasso regression. So I want to make sure one thing which we understand very clearly is, you know, uh, machine learning and artificial intelligence is something which, if you want to understand the entire maths and, or rather the arts and science behind it, okay, you have to dedicate a lot of time understanding, the mathematical concepts and the statistical concept, how that is derived using, derivatives. But whenever we look into the practical scenarios where we use it in industry, we would require typically the basic understanding of these, what these algorithms do, right? How we come across all these algorithms, which is the best one, right? And what is the logic behind all of these? Okay. But we generally don't tend to go to the mathematical part of it until and unless you are working a research project. Okay. In that you have to take, a different sort of approach to solve your problems and challenges. So for those who are from the non-technical background, you don't have to worry about if you come across, any of the technical jargons, either by me or, or by any other fellow student. You have to make sure that you understand the basic concept of it. Okay. Nobody in the interview, or even if you're in your career, okay, in my 7 to 8 years of my career, I have never, used this type of, calculations in the background, but I know what really goes behind all these algorithms, and how to tweak all the hyperparameters to make sure we get the best results. Okay. It's very tough to, go through all these statistical techniques one by one, do practicals with hand. This in this course, we'll try to make sure that we are interview ready, and there should not be a gap between what we are trying to understand here and what is actually in the practical world. Okay. Ideally, we have generally seen that whatever we had taught in academics is so deep rooted, we don't know how to, use that in our practical scenario. So we'll make sure that we understand the concepts, whatever is required, without going through much details, because it will, unnecessarily take a lot of our time and is not ideally required for 99% of our job work. Okay, we'll move on to the lasso regularization. What is lasso regularization? Why it is used? Um, Lasso is very, similar to ridge regression, but there are some differences between lasso and the ridge regression. Okay, the main behind idea is that by, slightly making a or introducing a bias in the data, ridge regression provided a long-term prediction by reducing the variance. Okay, by reducing the variance. So these are the concepts which will be asked in a interview. So whenever they say what is a ridge regression, right, you will ideally say that, even if though you don't remember the definition, you should be able to say that ridge regression is used as a regularization technique. Okay, you can take a pen and paper and say, if there is a steep line which basically fits well with the training data set, but doesn't work well with the um, testing data set, we introduce a small bias in the data. And that small bias is lambda into the slope square, lambda into the slope square. Okay. And when you answer this, the interviewer will understand that, you have that background and the basic concept of it. Now you can move on to say that this basically introduces a small bias in the data just to make sure that there is less variance. There is less variance in the testing accuracy. There is less variance in the testing. So instead of a steep curve like this, we are trying to reduce the steepness. Okay. Now ridge regression minimizes using lambda into slope square, right? And will so this is the ridge regression penalty, lambda into slope square. Now instead of squaring, if we take the absolute value, right, that is our lasso regression. Okay, if we take the absolute value of the slope instead of squaring it, right, we will have the lasso regression. So this is the ideal difference between the equation of ridge and lasso. So ridge, as I said, lambda into slope square, and in lasso you have lambda into slope, right? In interviews we have seen, some candidates, they are very well versed with the mathematical concept, that even if I ask them what is the ridge regression, they will, try to get into the entire mathematics behind it and try to solve equation. And particularly we have seen candidates who have, uh, a master's or a PhD, or they are doing research, which is the ideal scenario, that they have to go through this all these mathematical concept. But ideally for the roles which we generally hire, we don't require that type of, in-depth mathematical knowledge. If even if you have a mathematical knowledge, you have to make sure that you are able to explain this in a very easy manner, because ultimately as a data scientist or a data engineer or whatever role you have, a product manager, you have to make sure that you are able to, convey whatever you are uh, creating as a model to your stakeholders. And if you go to your stakeholders using these mathematical equations, they will probably freak out. Okay, so make sure that you try to understand the concept, and you are able to, answer the questions in as much vanilla manner as you want. Okay, can we use these for underfitting as well. Yes, I will come to that. Don't worry about it. Okay. So we have the lasso regression where the sum of squared residuals plus lambda into the absolute value of slope. Okay, this is the lasso regression. Now, just like with ridge regression, lambda can be any value from 0 to positive infinity and is determined using cross validation. So we will also go through what is cross validation, okay, both through Python as well as the theory class. So lambda into the slope, which is the lasso regression, and it is similar that the lambda value is going to be from 0 to infinity. Okay. Now, if we introduce a small bias, right, we will have a line which is less steeper, obviously, which is less steeper than the least square line. Okay, this is your least square line, and this is, for example, your lasso line, right, or lasso regression line. Now, this also has less variance than the least square. Obviously, if you see, you know, if we have this line, right? So this from the least square line, if you find the variance, it is going to be bigger, right? The difference between the predicted value, this is your predicted value, and this is the observed value. So P minus 0 or O, right? P minus O is obviously greater than, if this is your line, if I mark this as R, right? It is greater than your R minus O, right? So you can see the variance has reduced, right? For lasso as well. Now, these two remains very similar, right? The ridge regression and the lasso regression both remains very similar. Lambda into slope square and lambda into the absolute value of slope. Then what is the difference, right? They basically do the same thing. They do the same thing, but you can obviously understand that when we have lasso regression, we have a mod value or absolute value, right? And with ridge, we have a square value. Okay, so as we introduce square, it has more penalty. It has more penalty, or rather, we can say it has less penalty. Because if we say, for example, we have a value of -5 or a 5, for example, right? So ultimately, the answer is going to be 25. And here, if it is plus minus 5, the mod value is going to be 5. So obviously, there is a more penalty introduced. And that's why if you want to compare both of the lines, lasso regression line will be a little more steeper than the ridge regression line. But they similarly do the same thing, right? Now, both ridge and lasso regression can be applied in the same context, like this situation where we are using two different diets to predict size. Say, for example, if we have a categorical data instead of a norm of a continuous variable. So we have taken many mice and we have given different diets to both of them. For some of them we have given normal diet, and here you can see the size is increasing over time. And you have given some mice high fat diet, which increased the size more than the normal diet one, right? So we can use lasso and ridge in in same problem, okay, in the same context. Now, in this case, when we are taking an example of a normal diet and a high fat diet, our size is basically y minus intercept plus slope into weight plus diet difference into the high diet fat diet. Okay, so this is the line. So don't try to understand the line, but rather we have to understand that we can use both of them in the similar context. Okay, so ridge, lasso, linear, we can all use them with continuous variables as well. We will look into this in Python class, where we will convert a categorical data into a dummy variable, right, or encode this. Yeah, the last part is, I hope we all understood till here, where we are saying that when we have a linear, sorry, a ridge regression, we are introducing a square of slope, and when we have um, lasso regression, so this is ridge, we have lasso, right? So when we have a ridge, we are introducing a square of slope. When we have lasso, we have a absolute value of the slope. Okay, lasso will be less steeper, more steeper than the ridge regression, because since it introduces more penalty to the data set, right? And both ridge and lasso regression can be used in the same context, right? In the same problem or in the same data set, you can use both ridge and lasso. Okay. Now we'll come to this when we do the practical scenario. We'll be able to better understand it. Now, what happens is that whenever we introduce, a ridge and a lasso penalty, both, okay, it basically estimates the parameter except for the y-intercept. So ridge regression and lasso regression both basically works for anything apart from the y-intercept, right? So if you have y equals to mx1 plus mx2 plus c, right? So if we introduce a ridge regression or a lasso regression, it will basically work on both of them, right? But it will not work on the y-intercept, obviously, because there is no variable associated to it. Okay, this is what we are trying to say, that if we have a slope, right, slope into weight, this is, if this is my m1 x1, and we have high fat diet difference and the high fat diet, it will also, so if you say m2 into x2, so it will basically penalize both of them. Okay, but as we increase the value of lambda, ridge and lasso regression may shrink diet difference a lot more than they shrink the slope, right? So it means that, so the difference between these lines, these are the lines, right? So if, for example, if I say this is my line 1 and this is my line 2, so this is the difference between the diet, right? If you have two types of diet, normal diet and high fat diet, which you have given to a set of mice, and this is the difference between the diet which is given. So if we just took the average value, this is the average value, right? This is the average value. So if I take the difference, right, and I create an equation, something like this, right? Slope into weight plus diet difference into high fat diet, right? It means that as and when the value of lambda increases, right, the difference between the two, the difference between these two will also shrink, right? It will try to normalize it. Okay, we'll come to this again with the practical classes, don't worry about it. It's very difficult to showcase this type of examples through theoretical concept. Please repeat last part again, when to use L1 and L2 alone and together. Okay, yes, we'll come to this. So we have seen how ridge and lasso regression are similar. Let's talk about the big difference between them. Okay, when to use L1 regularization and when to use L2 regularization, right? Like the ridge and the lasso. To see what makes lasso and ridge regression, let's go back to the two sample training data. So we have only two samples. This is your least square one, least square, and this is your lasso. This is your lasso regression, right? And when we increase the value of lambda, just look into it, how if we increase the value of lambda, the steepness will also change, right? When we have lambda equals to 0, obviously, when we have lambda equals to 0, there is no difference between a squared residual and the penalty. So the penalty is ultimately 0. So if we have lasso has sum of square difference or sum of square residuals plus the penalty. The penalty is lambda into absolute of m. Now, if I have lambda equals to 0, obviously this is going to be just the sum of squares, and in that scenario, the least, this line, right, the red one and the orange one both are same because there is no difference, right? The least square and the lasso regression both are same. Now, if I change the lambda value to 1, you can see the value has changed. Right? The value has changed and the line has become less steeper, just like we had a ridge regression. Okay. And then when we have, values like 10,000 or 100,000 or whatever it is, we'll see the slope will turn to 0. There is no slope, right? There is no steepness in this line. That's why I'm saying slope is 0. The slope is 0. It means that the steepness has gone, but the slope is also 0. So there is no steepness. Okay, probably the worst line. So the big difference between ridge and lasso regression is that ridge regression can only shrink the slope, right, close to 0, while lasso regression can shrink the slope all the way to 0. So we all have seen the equation where we have, y equals to uh, x1 right. At the beginning of the class, we have seen some equation like this, right? So what ridge regression does is it can, change the slope, all of this slope to less, very near to 0, near to 0, right? This slope to near to 0, but it cannot, uh, make exactly 0, right? But with lasso regression, what we can create is we can have values which is exactly 0, okay, or very, very close to 0, and it will ultimately remove this type of variables which are not required or which makes the model more complex. Now, if we have a line segment like this, right, where you have y-intercept plus, weight, high fat diet, and then all of a sudden there is some variable called the astrological offset, or the speed, airspeed of the swallow, or the color of an umbrella, something like that. So whenever you have a data set, you might have data sets where you have, columns which are required for your analysis. For example, age might be required, height can be required, location maybe or may not be required, right? Your, say, astrological sign, right, not required, right? um, um, which hospital you were born, right, not required, or might be required, but in the context of that particular problem, right, these are some of the variables which are not required for analysis. And we have seen in the previous class that, as and when you introduce more and more variables, right, your r square and your adjusted r square basically tells you which are the important variables, which are not the important variables. And this will, with ridge and lasso, you will be able to find out which variables are not required. Okay, so this is the goal, ultimately, to find out the size of the mice based on, some of the factors. And you have weight and, high fat diet, which might be reasonable enough to, uh, predict the size. But again, astrological sign and the airspeed of the swallow will not be required, right? And will are not a correct feature as which can qualify as a good independent feature for your data set. Now we can remove this type of variables like astrological offset and airspeed or whatever it is, using the ridge regression. So and lasso regression. So the ridge regression, to the equation, we find the minimal sum of the square residual plus the ridge regression penalty, right? We find out the penalty which is introduced in the data set. And with that, we'll try to find out the optimal value of the slope and the diet difference. And the larger we make the value of lambda, these parameters might shrink a little bit, right? So this type of parameter will shrink. So with ridge regression, what happens is you are able to find, optimal values of the slope and the diet difference, and it will shrink. Okay, it will lessen. So as and when the value lessens, your steep graph will become less steeper. Okay, now these are the type of parameters which might shrink a lot, but there will never be equals to 0. As I said, with a ridge regression, you cannot make the value as 0. If you have make this value 0, we could have cancelled these. But with ridge regression, we can lessen this the effect of these type of variables, but cannot you know ultimately eliminate them. But in contrast, if we have a lasso regression, when we increase the value of lambda, these type of parameters will shrink a bit, right? It will shrink a bit, but these are the other parameters will go all the way to 0. So if we make it 0, what happens is 0 into sine will become 0, and this will also become 0. So this ultimately becomes null. Okay, so you can remove this type of unnecessary variables. So lasso regression can help you to select the features. Okay, ultimately lasso regression can help you to select the features. So we are left with size equals to weight and the diet, which is something required for our analysis, and we exclude the silly stuff here. And since lasso regression can exclude useless variables from equations, it is a little better than ridge regression at reducing variance in models that contain a lot of useless variables. Now you understand the difference between a lasso regression and a ridge regression. Now, ridge regression tends to do a little better when most variables are useful. So if you have already performed your variable selection, right, through any other method or methodology, and now you want to use a ridge regression or a type of regularization technique, then ridge regression might be useful. But if you use it in a context where you haven't performed any feature analysis, or you have removed any of your features, then in that case it is preferable to use a lasso regression, right? So now you understand the difference between both of them by equation, right? And the big difference is that lasso regression can exclude useless variables from your equation. Okay, and in contrast, regression tends to do a little better when most power variables are useful. Come on, Veena, Satish, Mayank, Harpreet, Hari, Bhargav, anyone? Okay, we'll move on to the first question. One second. The line of best fit or regression line is found when the sum of the squared residuals is minimum. Okay, not the sum of the residuals. Next one. If linear regression model perfectly fits, that is training error is 0, then right. So if your training error is 0, right, you cannot comment whether test error is going to be 0 or it's going to be non-zero, right? So there should ideally be there should be no comment. Moving on to the next one. In a simple linear regression model, if we change the input variable by 1 unit, how much output variable will change? So if your variable changes by 1 unit, it means it will change by its slope. Okay, we have seen this in y equals to mx plus c. So any change in the variable x will basically change the slope. The unit change will be in slope. Okay. Which of the following is true about adjusted R square? Is it larger than R2, R square? It is only used when there is just one predictor. It is usually smaller than the R square. If you remember the chart, it is usually smaller than the R square. As I said, R square increases even if you add any of the variables, but adjusted R square will not, increase. The value of the adjusted R square will not increase if the independent variable is not significant. Okay. Last one. The R square is the squared correlation of which two values? Little interesting. R square is the squared correlation of which two values? It is the squared correlation of the y and the predicted y value. Okay, so why it is so? Because whenever we are calculating R square, we are trying to, uh, find out what is the correlation between the predicted value and what we have already, observed. And we'll come to this in the next session as well. So, okay. Good job, Hari. And we'll move on to the next question set. Only two. Please use the chat window. Only four. Waiting for two more participants. Please, guys, join. Okay, let's start. For ridge regression, if the regularization parameter is equals to 0, what does it mean? No. So overfitting problem are not accounted for. As I said, you know, if the regularization parameter is 0, the least square and the ridge regression line both will be same, and it will try to overfit the data points, right? So this means second will be the correct answer. Overfitting problems are not accounted for. The last one, what is the penalty term for ridge regression? What is the penalty term for ridge regression? Ridge regression is square of the magnitude of the coefficient, not the absolute. Absolute for lasso, right? Okay, so with that, we'll move on to our Python exercise. Okay, okay, please open your Jupyter notebook and go to the uh, Google Drive and download the data set which is present there. Melbourne Housing Full.csv. Please open that. I will share this data set with you. Let's try to. Okay, so I'm creating contents for your interview preparation. Okay, once all of these, one by one, I will try to share with you. And with that, I will move to. Right. So we will look into something uh, related to ridge and lasso. Just want to make sure that we know how to perform ridge and lasso using some of the libraries, and before that we will import one of the data set which is already present in our local. um, so let's start by importing some of the libraries. We'll import numpy as np. I will import matplotlib dot pyplot as plt. Import pandas as pd and import seaborn as sns, right? Panaras. Okay. Now try to import the data set. Import data set by using dataset is equals to pd dot read underscore csv, and we can give the file name here. Here we go. Name. Right, we'll just quickly see the data set. So this is the data set which we have, right? It's better to print the head. Please share the drive location. Okay. Can someone share their drive location or chat, please? Okay. Thank you, Hari. I'll give 1 minute to Satish to just download the data set. Just looking to done. Okay, great. So just look into some of the number of unique values. So you have suburb, 351 unique address. Okay. Rooms type, price, method. Okay. Just looking into some of the descriptive features. Data shape dot shape. Yeah. So 3487, 21. So there are some missing values also. Let's see, or may not be. Right. So if I want to take data into my analysis, let's try to identify some of the columns which are required, and let me quickly open the file. Okay, suburb, address, room type, price, method. Okay, that's fine. So we'll move to our, and let's try to create one custom column with the columns which we want to use, and we'll see how to do this, without selection. So some of the columns which we might require is, for example, suburb. Right. Please follow along me. Try to do this type of practicals along with me. Type with me, so it will give you better revision. It's better to do the practical simultaneously rather than taking time to again say it and then run the codes one by one. So address is not required. I will not take address. Let's see if type works. Method price will be the target variable because we are trying to predict the price, right? So method is required. I can also delete it. That's not a problem. If you want to use a delete function to delete some columns, not a problem. Cell G. Right. And then I can take the region name. Anything else? We have property count as well. Okay, all these points are required. My bad, could have deleted it. So postcode will be required. No, address is not required. So council area. Yeah, bedroom, bathroom, all are required. So I'll just quickly take this as it's already started. Bathroom. Next time onwards, I'll try to delete it from the data frame itself. Car, and then land size. Okay, let's take the last one as the price. Bedroom 2 is listed 3 times. Is it bedroom 2? I can see once. Okay, in the list we created bedroom 2. Oh, okay, my bad. Okay, so I'll take these as the columns to use, and then let's see. So the data set which I will create will be is equals to data set, and then we can just copy this, right? Land size. Right, I'll just copy paste this. Really sorry for this. Okay, so the land data set is created with the ones which I require. Okay, so now we have 13 columns, and yeah, data set. We'll try to find out if there is any null value. So is any, and the sum of it, right? Okay, suburb has 0, 0, 0. Region name has 3. Property count 3. Distance 1. Council area 3. Okay, bedroom 2. Car. Okay. And size. There's one more variable which we can add. Building area, because it has a lot of points. Let me just quickly add this building area, right? I just added the building area column to the data set, right? I will close this, not required. Yeah, building area has a lot of is in a sum. Okay. Now we need to do something about these NA values. So let's fill them with 0. So the ones which we require is property count, price target variable as well. No. We'll we'll look into the columns which we find, it should be filled with 0. Okay, so columns like, property count, the distance, right? Distance we need to fill with 0. Bedroom to bathroom, car, we'll fill this with 0. And rest of all, so this is just the EDA technique which we'll do for some of the columns, and the rest of the columns we can put mean values, right? So let's start with the property count, because there is no point putting mean values for only 3 data points. So we'll change this to 0. And then distance. If you want, you can delete also. I just don't want to delete them because might bedroom 0, bathroom. Shall I make it 0? Let's make the car 0. Okay. Okay. And now we'll try to fill this to data set, and then column to fill 0. Right. I will try to assign the values equals to data set, columns fill 0, and then dot fill NA 0. Right. Now if I do the same thing, now with land size and building area, I don't want to fill them with 0. What I will do, I will try to put the mean to it, right? Data set, because these might be important variables. This is something we should check the distribution of. Yes, you can check the distribution. I just wanted to, in the EDA, we will focus on, visualization part, but here I'm doing some data imputation just to make sure that we all understand how to perform, fill missing values with zeros, or fill the mean values wherever there is no data point. You can do the EDA as well. In the last class, we have extensively looked into the EDA part. We didn't look into this type of um, EDA. So I'm just doing this now. And in the next class, we'll do the end-to-end regression. We'll go through all of them. Just the basics I want to cover for people who are not much confident with EDA, and basically we come from the non-technical background. So if I want to do this for land size, okay, we'll do data set, and length size, right? And we have to fill the NA values with data set. I hope this will work. So what I'm trying to create is I'm basically going to the data set data frame. I'm going to the data frame and then the land size column, and wherever there is a NA value, I am filling all those with the mean value of the existing land size value. Okay, and I'll try to do the same thing for building area as well. Land size. Right, try to paste this again. See, now region name is not required, so I'm not taking into that consideration. Council area, I don't think is much of an importance. So if you want to, you just make it 0. Okay, just the way I want to showcase you. And then we will move on to the price point. So here, what we can do is we can use dataset dot drop NA, right, in place equals to true. Okay, so what I'm doing is now that all that imputation is done, wherever required, I have put the value 0 for some of the data points, and wherever required, I have put mean to some of the columns, right? Both of them are done. Now, wherever there is no data or there is a NA, I will quickly remove them. Okay. Since price is something which we are going to predict, we obviously won't impute that. Okay. Impute means we cannot, fill the values with NA values with mean, or we can replace it with, median or mode or whatever it is. So we cannot do anything with the dependent variable. So we will remove wherever we have a NA value now, right? So if I just
Yes, NA is bracket.
yeah. So now you can see all of them have no NA values. Okay, so we looked into 3 type of imputation. First is where we will replace the values with 0. Okay, this is specifically for those who are newbie with Python. So I'm replacing NA value with 0. So I have taken some of the columns. If you wish to add, there were some more. If you want to add, region name and council area, you can add that, not a problem. Okay, there might be a small difference in the accuracy, but that's okay. And then in the next step, what I have done is I have replaced some of the values with the mean value, because land size and building area is somewhat, very much related to the price. So I have imputed this with the mean value. Okay. Next is I have dropped wherever there was a NA. So there you see the price has NA, council area has NA, and region name has NA. So wherever we have NA, I have dropped them. So there are 3 imputation techniques which we have used here. And with that, we will, look into some of the variables. Say, for example, if I just quickly look into the data set, you see seller G, region name, right? Council area. These are all categorical values. And whenever we are performing any type of linear regression or classification technique or any machine learning algorithm, we basically convert all of these to NumPy arrays. And NumPy array only, as the name suggests, numerical Python only understands numerics, okay, or numerical data. It does not understand any, categorical data. So for that, we need to encode this, okay. And for that, we will use something called the get dummies to convert all of these into dummy variable, that is zeros and ones. Okay, let's see how we can do that. So data set equals to pd dot get underscore dummies. Okay, get underscore dummies, and we will pass our data set, right? And it will drop the first value equals to true. Okay, I will come to what is dropped first is equals to true. And then we'll print data set, say head. Now you can see that, seller G or the column suburb, for example. Okay, it's not showing all the data. Suburb, yes. So now suburb G has changed to something called zeros and ones. Council has changed to zeros and ones. Okay. Now, for those who don't know what is get dummies, I will quickly create one slide. Right. Now, for example, if you have a categorical variable, say for example, age or sorry, gender. This can be male or female. I am taking just 2 examples. Okay. And if you have say 1, 2, 3, 4, 5, and if I say male, female, female, and male, right? Now we can change these to dummies, okay, which is also called encoding. We'll come to something called a 1 hot encoding and 2 hot encoding, right? But for now, try to understand that if I create a column, say gender underscore M and gender underscore F, right? 2 new columns are created. In M, wherever there is a M, I will put 1, and wherever there is a F, I will put 1, and rest of them will be 0, right? This will be 0. So what this get dummies does, is if it has any categorical value, it will first count the number of categories. Okay, say for example, it has only 2 categories, male and female, so it will create 2 columns for you. Had there been a transgender as well, right, it would have created male, female, and then a transgender column as well. Okay, but for now, try to understand that we have only 2 columns. We have only 2. Okay, we have only 2 values in this data set, and with the drop underscore first is equals to true, what I'm doing is I am dropping this. Okay, I'm deleting this. See, even if I delete this, you will be able to understand that how many males are there. If gender for female is 1, right, obviously the other one will be male, right? So this becomes a redundant column, right? So this is not required. If you have two, I don't know why my pen tab is not working. Okay, so if you have, instead of two, if you have male, female, and transgender, you can say, one column is male, one is female, one is transgender, and you can put 1, 1, 0, 1. Okay, so you can put male as 1, 0, or rather you can create combinations out of it, right? If there is male, you'll have, two zeros. You have two, 1 second, 1, 0, 0, right? 0, 1, 0, and you have 0, 0, 1. Okay, and then you can remove this first column because again it becomes redundant. Just by looking into two of them, you can say whether it's a male or a female or a transgender, right? Obviously, when there is two zeros, you have male. If you have 1 and 0, you can say this is female, and when you have 0 and 1, you can say this is a transgender, right? So you have three notations to denote all of them, right? And with only two columns. Okay, only with two columns. So that's why whenever we use a get dummies, what we do is we use drop underscore first is equals to true, because the first column becomes redundant. Okay, not required. Right? Any question? Okay, let's move on to the next one, where just create the variables. Say for example, I create x is equals to data set dot drop. I will drop, say, price. I have to pass x is equals to 1 because I am performing the computation on column, right? And I will also create a variable y, which will have only price. Right? X and y. Now we all know that if you want to do lasso or ridge, we have to basically do the linear regression problem, right? So quickly import from sklearn dot model underscore selection, right? Oops, sorry. Import train underscore test, right? And then we will create some variables for train. I will just copy this. Right, I have to pass the variable x and y the way we did in the last class. Let's create test underscore size is equals to 0.25. Okay, and create a random state. If you want to replicate my solution, you can give the same random state as mine, right? And the split is created. Now we'll import the logistic regression function or package. Sklearn dot linear regression or sorry, model, import linear regression. Okay. Do let me know if you're not able to follow. Right. I will create the prediction in REG, linear regression, and then we'll try to fit, right? What we generally fit, we fit the train X and the train Y. Right. So what we did is we have first splitted the data into training and testing. Okay. And then once that split is done, we will import linear regression and try to fit the training data set onto the linear regression model. Okay. Now let's try to get the score reg dot score test underscore x. Okay. 0.66171. So this was my testing score. If I calculate the training score, right, the training score is 67.0888. Okay, and now we will try to do this with the regularization technique. So you can see obviously here that the training and the testing is not too much. There's too much. There is no variation, I would say, between the training and the testing. So regularization might not be that useful, right? But we'll try to tweak the data to make sure that there is some overfitting. Let's see. Okay, so how to do this with lasso? Mm, we can import linear model. Okay, so import linear model, and then we can look into something called lasso. Just creating a variable lasso underscore regression linear underscore model dot lasso, right? We'll pass a random value of alpha, say 50. Okay, you can pass whatever value you want. Max underscore iteration is equals to 100, and the tolerance is 2.1. So these are some of the parameters which I'm using, and I will just explain it. Okay, we have used alpha 50, max iteration 10, and tolerance 0.1. We'll just find the score. So instead of regression, I will use the lasso regression. Right, so nothing has changed much. It has hardly changed from 0.661 to 0.666 a bit, because it was not overfitting the data. Okay, and it remains the same for ridge regression as well. So I'll just copy paste. There's no change as such. Right, instead of lasso, I will do ridge, and then
I get an error saying lasso attribute is not available in the module sklearn linear model. sklearn linear model.
lasso.
There is no attribute lasso in sklearn linear model.
Have you given L as capital?
No.
Yeah, you have to give L as capital.
Okay.
Yeah.
Thank you.
Yeah. Okay. And we'll try to find the score with ridge. No, ridge gives you 6.65. Okay. Let's try to do something with the data so that it overfits. So now that you have seen how to implement lasso and ridge regression, let's look into some of the parameters which are present here. So alpha is basically the lambda value which we want to introduce, and in this class we will only look into one of the static values, 50. In the next class, or rather I will share a Python notebook wherein I have used a list. Okay, it basically goes through the values from starting from 0 point something up until a value. Okay, and it iterates through it and finds the best best fit line based on ridge regression or lasso regression. The number of iteration is how many times you want to iterate, or how many times you want to create one of these lines, right? And for the tolerance is basically uh, the stopping criteria. Okay, this tells the sklearn library to stop searching for a minimum or a maximum, whatever it is, based on the calculation which we did, right? The minimum or the maximum. And once that tolerance level is achieved, and we are very close to that particular tolerance level, we stop there. Okay, more about it when we look into the gradient descent algorithm. I will come to something called a learning rate there. But for now, we have to understand that ridge and lasso regression tries to find out if there is any underfitting, overfitting scenario, and it tries to regularize the data. Can we do something with the data to make sure that we get some bias? Okay, I don't think this will. Okay, just try to introduce one more, and I am testing set to 50. Now you can see that now that I have, increased the testing data set to 50%. So now it is getting tested with very less amount of data. Sorry, trained with very less amount of data. That is just 50% of the data. And with that, the regression score comes to somewhere around 57, right? Which is the R squared value here. It comes to 0.57. And when we do this on training, we get at 68%. So you can understand, whenever your training accuracy is better than your testing accuracy, it means that it has overfitted the data, right? It has overfitted the data. I'll try to do something with lasso regression, and this 57 is now a little better to 58, and with ridge we are getting 56. So this means that as and when, if we train the model with less amount of data, it will try to overfit. If you wish, you can make it 0.7 and train it again. You'll see that the testing accuracy and the training accuracy is different, quite apart, right? And what lasso will do is, so we have to find the optimal value of alpha and run it across to make sure that we are getting somewhere around at least 65 to 70% accuracy with this level of um, lasso parameter, lasso and ridge parameter. Right now you can see from 62 it has become 62, and obviously the parameter which we have provided statically is not the correct approach, but rather we should do something with incrementing this alpha parameter and iterating it over time. We'll look something with something called a grid search, and that will eventually tell us that which is the ultimate value of the lambda, which penalizes the model for the training bias which is introduced. Okay, so in the next class what we'll do is we will start from here where we have completed, and we'll look into more of uh, how we can create a learning rate to make sure that linear and lasso works pretty well, right? So now you understand what is the linear, sorry, underfitting scenario and an overfitting scenario. Underfitting scenario is where you have, um, the model is very simple. Okay, when the model is very simple, we call it a underfitting scenario. Right. So whenever you have a underfitting scenario, it means it is a very, simple, or the model complexity is very less. When you have a overfitting scenario, the model complexity is very high, right? If you want to, reduce um, the overfitting or the underfitting, to make it optimal, what you need to do is you need to increase the complexity. The complexity of this model needs to be increased, right? As and when the model becomes more complex, it goes from underfitting to a overfitting scenario. Okay, and we have to basically find a balance between both of these, the underfitting and the overfitting. Why underfitting happens? Underfitting happens because the number of features, say for example, if I just want to predict the height from the age, right? So age is only one feature. There might be other features as well, like genetics, right? The area view where you belong to, right? Or whatever the other features. So if you increase the number of features, your underfitting accuracy or your model will become more balanced. And as and when you add more number of features, it tends to become overfit, right? Because the model will try to, um, um, please all of its feature points, right? There might be instances where if you want to move from underfitting to a balanced um, data set, you have to, remove some of the noise in the data. So you can clean the data, impute the data, remove any garbage values in the data. And uh, in we will come to something called the cross validation technique, where the number of epochs or number of duration you do the training is increased. With that, you will also be able to reduce the overfitting and move towards a balanced data set, right? So now we understand that whenever we have a overfitting scenario, we try to do some regularization to make sure that the steepness in your data point or the best fit line can be reduced, even if we introduce a small bias in the data. Bias, you can say error in the data, which eventually will help in reducing the variance. In the last class, we have understood what is the bias variance trade-off. A bias variance trade-off is where you try to balance the bias and the variance. Okay, so that's okay. I have a question. Can we combine ridge and lasso in coding? Yes, you can combine. That's not a problem. But they are two different, use cases as altogether. You can do that. That's not a problem. Okay, so we generally, combine two machine learning algorithms together also. That's not a problem. So you can combine ridge and lasso. Okay, but ultimately you have to uh, understand that there is one more regularization technique called elastic net. I will go through that in the next session. And with that, you will be clear, if there is anything which you can do with elastic net can be balanced off both ridge and lasso. Okay, so with that, we will close here. If you have any question, do let me know. People are coming to the WhatsApp chat to solve any type of difficulties they have. Um, I will try to create, the statistics cheat sheet as well as the questions and as soon as possible and share with you. And in the next class tomorrow, we'll go through some of the statistics question to, brush the the concepts again so that you don't forget it. And we'll try to complete k-fold classification, gradient descent uh, in the next class, followed by end-to-end regression scenario where we will predict, some numerical data or continuous data um, for any of the problems. Okay, thank you guys. Thanks a lot.